Next speaker is Arun Kannan. He's going to talk about frequency stability analysis for inverter-dominated grids during system splits. I'm going to play the presentation, but it's going to be available for questions and answers at the end. Arun has completed his bachelor in electrical and electronics in 2010 in Mysore, India, and then he has been working at power system engineer in Bangalore, India, after which has moved to Germany, and he has since then been working at the Fraunhofer Institute of Energy Economics and Energy System Technology in Kassel, Germany. He's now on leave at the EPRI, Electric Power Research Institute in Knoxville, USA. His research focuses on power system stability and control for high shares of inverter-based generation and microgrid analysis. Okay, let me share the...
Hello, good morning everyone. My name is Arun Kannan. I'm working at Fraunhofer IEEE in Kassel, Germany. I would like to present my work on frequency stability analysis for inverter dominated grids. This task is performed under the project Netzregelung 2.0 supported by German ministry. Here are the contents of my presentation. So first I'm going to discuss about the introduction and then I'm going to discuss what would be the main focus in this presentation, and I'm going to discuss what are the different modeling approaches I have considered in the studies, and followed by in case studies I'm going to discuss the results that I have obtained from the different modeling approaches, and at last I'm going to conclude the presentation. Let's start. So the first part will be the introduction. Due to global warming, the whole world rapidly increasing the inverter-based generation. So due to this, in future, with the replacement of conventional generation, and the power system dynamics are determined by inverter control. So you can see from this 2016 forecast of the highest hourly penetration of inverter-based generation in Europe by 2025, you can observe there are certain times regionally up to 100% inverter-based generation can be observed. For example, in Germany, Denmark, Ireland, etc. So in future, you don't expect not only generation but also the load becoming inverter coupled in future. Next is objective of this presentation. So due to increase in inverter-based generation by replacing conventional generation, so we know the whole total system inertia is going to reduce in the power system. So it is important to investigate the frequency stability for a large disturbance cases such as system split. What's going to happen? So I'm going to discuss this by using two modeling approaches. The one would be the extended load frequency control model. So this is developed by using MATLAB or Simulink, and another one is detailed dynamic grid simulation model. So this has been developed using excellent power factor software. So I'm going to consider to analyze these models using the evaluation criteria such as rate of change of frequency, which should be within 2 Hz per second, and under frequency limit would be 47.5 Hz, and at the same time over frequency limit would be 51.5 Hz. So these are the limits are considered based on ANSOE grid code. Different modeling approaches. Before going into the extended load frequency control model, so we have to understand what is the conventional LFC model. So in the conventional LFC model, it contains three parts in it. One is aggregated rotating mass, which is nothing but the inertia, and the second one is self-regulating effect or frequency dependent loads, and FCR, which is nothing but frequency containment reserve or primary frequency control, which is provided from governor. So you can see the response if there is any active power disturbance in it. If I have only inertia in the system, then the frequency is going to come continuously decreasing. That provides initial imbalance will be taken care of. But we need, if I have some along with aggregated system inertia, if I also have self-regulating effect, then the frequency would decrease and it remains constant. In order to recover it back, in order to bring it back to the quasi-steady state value, we need a proportional control, which is nothing but FCR. This conventional LFC model has been extended by considering the transfer functions of grid supporting inverters with a current controlled behavior, and then the grid forming inverter with a voltage controlled behavior. So the detailed explanation of these transfer functions are explained in our previous publication. So I would like to concentrate in this presentation by explaining the other two functionalities. The other one is under frequency load shedding, and the second one is limited frequency sensitive mode over frequency. Main aim of the under frequency load shedding scheme is to prevent further decline of frequency during large disturbance. So there are different steps normally involved to activate this under frequency load shedding scheme between 49 Hz and 48 Hz. So in this analysis, we have considered the activation of this under frequency load shedding scheme from 49 Hz till 48.1 Hz. In step of every 100 millihertz, 5% of the load has been taken off. The next functionality that I'm going to discuss is LFSMO. The main aim is to provide the power reduction of the generating units with certain time delay if the frequency goes beyond certain threshold. This is a control block diagram of LFSMO. So whenever there is a disturbance, initially the frequency is measured, and then if the frequency goes beyond the frequency threshold, then based on the droop that has been considered in this case, the power activation has been done to curtail the generating unit with certain first order delay. The parameter that has been considered for this control block diagram parameters has been shown in this table. So just for highlighting, the frequency threshold has been chosen around 50.2 Hz, and the frequency measurement delay is around 20 milliseconds, and droop has been considered as around 5%. This is a detailed dynamic model considered from TSO test system. We can see here the aggregated synchronous generation that has been placed very close to aggregated load, and two inverters that has been placed at a distance of around 50 kilometer, and external grid will be opened in order to create a system split scenario, and then in order to increase the inverter based generation, the synchronous generation capacity has been reduced, and the load variation is performed in order to create disturbance, and the inverters that has been considered in this case are from VEC generic PV model. And the one more point which is very important is all the loads has been served in this case only by inverters, and synchronous generators provides only inertia. Next is case studies. We have performed two types of case studies in this. One is under frequency and another one is over frequency. Under frequency is performed with 60% export, and over frequency is performed with respect to 40% import. Both of them is with respect to injected power, and these two case studies are repeated for both constant power and constant impedance load type, and all the scenarios are performed by varying the inverter based generation from 10% up to 90%. The above case study that has been discussed is performed by considering extended LFC model and detailed dynamic model. I just want to make up one point here. The extended LFC model is performed only by considering constant power load model, and what is not considered in the simulation is frequency containment reserve from synchronous generator and self-regulating effect of the load. These two are very negligible during large disturbance such as system split, and here we are also not considering initial response from inverters. And the main focus of this case studies would be only concerning short-term frequency response. This is a case studies of low frequency situation for the extended load frequency model with 60% export scenario. I have performed here the case studies with inverter based generation from 10% to 70%. The above in the figure above shows the frequency, and the bottom is active power of inverters in gigawatt. And you can see here the maximum rock-off and maximum instantaneous frequency deviation is increasing with the increase in inverter based generation, and this is due to the reduction of inertia. And for inverter based generation less than 60%, the stability limits are within the limits. However, the frequency stability limits and as well as the rock-off limits are exceeding for the inverter based generation equal to 70%. This is a case studies with detailed dynamic model with 60% expert scenario by considering constant power load. You can see here the fast frequency dynamics which is observed in this scenario is very close, similar to what we observed in LFC model. However, the frequency stability limits are exceeded for the inverter based generation, that is greater than or equal to 80%, and the rock-off limit is exceeded for after inverter based generation reached greater than or equal to 60%. This is the detailed dynamic model results with constant load, in constant impedance load. In this case, we have performed inverter-based generation from 10% to 70%. Beyond 70%, the simulation cannot be performed due to computation problem. And we can observe in this case, the initial transient peak is lower compared to the constant power load. This is because during the low frequency scenario with high generation and low load, voltages tend to increase in the grid. In order to keep constant impedance, the load current will also increase. This which implies the active power is going to increase, and this results in the effective reduction of the overall disturbance. You can see the rock-off limit exceeds after inverter based generation more than 60%. This is a comparison of different models. I have chosen 60% inverter based generation in this case. You can see LFC model and dynamic constant power load has very closely matching dynamics. However, dynamic model with constant impedance type has slightly different transient response. You can also observe from the table what is the maximum frequency observed in all the three scenarios. As we observed from the two different models, the frequency response tends to deviate for the inverter based generation beyond 60%. The reason is frequency measurement method and the location. In the detailed model, the PLL transiently affected by system split and jumps beyond 50.2 Hz. Because of this, the power reduction starts after split without delay. In the LFC model, I am considering aggregated generator speed in order to measure the frequency. That's why we do not observe any transient fluctuation in it. This is a comparison of different models. For this scenario, I have considered 40% inverter based generation. You can observe from this figure that dynamic frequency response are closely matching in all the different models. However, the frequency response tends to deviate after a transient period. You can see for LFC model with no losses and the dynamic model with constant load power type, which is red and blue dotted, which has slightly different transient response. This is due to the additional 5% load shedding. However, if I consider LFC model with losses, then both dynamic model and the LFC model has same number of load shedding steps but delayed activation time. You can see for dynamic load with constant impedance type has slightly lesser load curtailment and in comparison with dynamic constant power type. This is because the load will reduce due to decrease in frequency. And you can see at the bottom of the table, this is a minimum frequency what you can observe for all the different scenarios. In the conclusion of this presentation, So we discussed two different modeling approaches. One is LFC model and another one is dynamic load model to analyze the frequency stability during system split. And we are observed that the LFC model can reproduce the behavior of the grid by considering constant power type much accurately. And the extended low LFC model is a simplified approach, and it is accurate up to 50 to 60% of inverter based generation with very high uh, power imbalance. And for future grid scenarios with very high inverter based generation, this model can still be applied to understand the general trend of frequency stability. From over frequency situation during system split, the different stability margin is detected using different modeling approaches. From extended LFC model, we could get a very good estimation on frequency behavior for very large disturbances with inverter based generation up to 50-60%. From dynamic model, what we observed is the PLL dynamics can't be captured with the help of RMS simulation. So from under frequency situation during system split, LFC model closely matching with dynamic model for inverter based generation up to 50% within 11 time frame. The frequency recovery, however, differs for different simulation approaches. So for high inverter based generation, the used WEC model might lead to numerical instability of the dynamic simulation. Therefore, the improvement for this would be to use voltage interface VEC model. So that has been proposed in this reference. So yeah, thank you very much. If someone is having a question, please, you can write me an email. Thank you. Thank you very much.
Thanks a lot, Arun, for preparing this presentation. We have a few minutes for questions. I think there's a question right now in the question and answer panel. You're, of course, welcome to address it.
Yeah, thank you very much. I could see the first question is, do you have some reference for 5% load shedding for each 0.1 hertz? Yes, I have a reference for this. I already referred it in my paper. This is based on the reference provided by the ENSOE report. I think you can see my paper, you get the information on that. And the second question is, are there any special consideration to be taken in the modeling of the frequency and Rokoff measurements by IBG and their park controllers? I would say yes, because the Rokoff measure, especially for the Rokoff measurements, where you can measure it with the time frame of 100 milliseconds or in step of 200 milliseconds, you get different values. So there are some references which you can see. One is from Ireland. They propose to consider the Rokoff measurement of around 500 milliseconds, where you can observe during the disturbance not so high value. So because if you use very small time frame, then you tend to get very high values. So we should have some kind of uh, balance so that we don't over measure it. So, and are there any other question?
If not, then thanks again, Arun, for the interesting presentation and for being with us to answer questions. That's very appreciated.
Yeah, thank you very much. It's just because of the time lag, I couldn't give the presentation on time. Yeah, thank you.
We completely understand. It's a common issue for most of you. It's a pleasure to have everybody connected despite that.
Yeah, thank you very much. Yeah.